as we move along with our research, sometimes it's necessary to do some transformations in the data, some recodings. Here I'm going to show you how to do recoding of a variable. In this case, I'm going to use the GDP per capita, and I'm going to create different income brackets from that. Let's start with the basic descriptive statistics. So the sum command or summarize command, and then you put a variable in front, gives you the basic descriptive statistics of the variable. If you add the option detail to that to the summary statistics, you're going to get a more detailed, so to speak, levels of description. So in this case, I'm going to get the summary of GDP per capita. Since GDP per capita repeats the same value within countries for all the time, so I'm just going to select the last value for all the individual countries. So in this case, I'm just going to run the summary statistics. This is how can you subset without actually creating a new variable, a new data set. So I'm going to just run the GDP per capita only if the date is equals to this TD function is time daily, and you need to put it in the format that is in the data, 31 of August 2022, with the option detail. So this is just going to make sure that selects, basically doesn't select the duplicated values for GDP. And this one, the detail, unlike the first one, it gives you a little bit more information. It gives you the percentiles distribution. It gives you still the mean, the standard deviation. It gives you also the variance, the skewness, kurtosis, so on and so forth. So I'm going to use this to actually create the buckets in my recoded income variable. So the recode command starts obviously with recode. You can type here recode for more information, and then you put the name of the variable. And after that, you open a parenthesis in which you are going to start creating the buckets. So based on this distribution, for example, I can see roughly that under around 25% of the data, the levels of income is close to 2,000. So I'm going to create my first bucket to sort of like get the lowest the first quartile, or the lowest 25% group in here. So basically from 0 to 2,000 is going to be 1. And I'm going to say, okay, I'm going to add a label. This is less than 2,000. So if I go back to my summary statistics, if you notice, somewhere between 2,000 and about 16,000, it covers pretty much the middle half of the data. It's roughly what is called the interquartile range, which is between 25% and 75% of the data, basically the middle section of the data. So that is between 2,000 and 16,000. So I'm going to use the second bracket or bucket for that. And I'm going to call it greater than 2,000 all the way to 16,000. And then the third bucket is going to be from 16,000 to 43,000, which is basically from 75% all the way to 90%. Right? And then the rest is going to be the same, only for 5%. So using that criteria, you can use any criteria you want. So here I'm just trying to aggregate data into groups that make sense. Once you finish creating the buckets, anything that doesn't fit or doesn't follow this criteria, you can send it to missing. And then there is an option here again, comma. We're going to create a new variable called income group. So all these are going to be recorded into this variable. And the labels, these labels in red that we're seeing here, are going to be saved in something that is called income group. I'm going to also add a label variable to the income group variable. So it's going to be called GDP PC recorded. And I'm going to get some frequency. I'm going to make sure you save your do file. I'm going to run this. And here is the variable. This is what the recorder did, no errors in there. This is the label of the variable. If you go down to the variable, here's the label, and this is the variable. And this is the frequency. So basically, we can see about 25% of the data is less than 20,000. 2,000. Between 51% of the data is between 2,000 and 16,000. 14% of the data is between 16,000 and 43,000. 5%, almost 5%, are between 43 and 56, and greater than 56. So if you do look at the cumulative percentages, basically 3/4 of the data in this for these countries are basically under 16,000. Since this is a categorical variable with labels, you can also you can see the numbers that are behind the labels without. So in the example above, you can see the labels. In the example below, you can see the numeric assignment. 1, 2, 3, 4, 5. It allows you to see. And now that we have this graph, we're going to use the same, the similar format that we did before with the scatter plots, by removing the markers and just adding the name of the countries. So let's do that for cases. Depending on the computer power of your laptop, this might take a little while. So here basically we have different income groups, and we can see what could be possible the outliers. So sorry about the low battery. So here we can see, for example, in the bucket between 2,000 and 16,000, which is basically the center data, it looks like the Marshall Islands had a little more cases in there. In the 16 to 43,000, Israel seems to have a little more cases. We can see on the richer countries, we can see Iceland and Netherlands and Denmark to be on the higher end. So you look at this, and you can start making your own inference. That's for cases. Let's see what happens with that. So in the case of that, we have a few possible outliers: Grenada, Bahamas, Luxembourg on the richer one, United Kingdom on the poorest one, Kyrgyzstan. So yeah, look at the graph and then start making. You can also do box plots. For this particular data, the box plots are a little weird. But if you want to do box plots, the command is graph box, and then is basically the variable that you want to plot over. So in this case, you cannot put it in the same line before the option. So the option over allows you to say, okay, I want to do it per income. And then you can add labels to them with this marker option. So it's going to take a little while on this machine. So you want to do it on your own, just be patient. It takes a while. So those are basically the basic recoding of the variable in terms of the income group. We're creating a categorical variable. Now that we have these groups, what we could do is we can start exploring, doing some inferences by comparing the average across those different groups. So we know that there are different sample sizes. The question is, on average, the mean values that we see across all these type of these 5 groups are similar to each other or not. For that, we can explore, or we can use what is called one-way ANOVA. So the one-way ANOVA compares the mean across different groups. Usually applies to more than 2 groups. So the null hypothesis in the case of ANOVA is that all means are equal. The alternative hypothesis is that at least one of them is not. So in Stata, the command to run one-way ANOVA is actually called one-way. The format, the syntax is you put the variable, the quantitative variable first, and you put the grouping variable second. Now, to make it more functional, to make the output a little bit more useful, we can add the options after the comma, when the function will tabulate, and the function Bonferroni. I'm going to explain what this is. So I'm going to run this line, and it gives us this output. So the output starts here. The command starts here. And what it does is basically the tabulate option gives us a little bit of summary statistics. So basically this tells you, okay, so this is the mean of daily cases moving average per 1,000 people. For less than 2,000 is 0.82. Between 2,000 and 60 is 13 cases, 41 cases for 16 to 43, so on and so forth. So the question here that the ANOVA does is, statistically speaking, is this 13 different from this 41? Is this 41 different from this 35? Is this 41 similar to this 40? So in terms of the averages, right? So the actual ANOVA output is this table right here. And what you do is you look at the last value, the p-value, and this shows you what is the probability that all means are equal to each other. And the probability that all means are equal to each other is 0%. So basically what you are concluding here is that at least one of them is not equal. So the ANOVA table itself doesn't tell you which one is different. What it tells you is that taking into account all these 5 groups that you are giving me, there is at least one that is different in terms of the means, right? And then the Bonferroni option actually does a little bit of work for you, because it goes back into the data and then tests the means by pairs, right? And that's this output right here. So, and this is useful because once you find that this is significant, then the question is, okay, which one is different? So here you compare the group number 1, less than 2,000, versus group number 2, 2,000 to 60,000. The mean difference is 12, and that's significant. The difference of doing this as opposed to doing the t-test is that in this case it accounts for the number of tests that we do because we have 5 groups, so you compare 1 to, we are making all these number of tests. So basically the p-value gets actually spread out in these tests. Now we are comparing the group number 2 versus group number 3, also significant. This is the difference. Again, so this is the p-value. In general, if you look at the p-values, all of them are significant differences. Basically, all the means are significantly different from each other. So there is one, for example, is group number 3 versus group number 5. So 1, 2, 3. So the difference is basically 0.44. If you notice, this is not significant. This is not 0, it's actually 1. So that means that groups number between 3 and 4, the means are not statistically significant. The other ones seems to be significant. So let's do the same thing with that. The same thing. The table here is just the means. Tells you we are testing those means. At least one of them is significantly different from each other, since we don't know which one it is. We look at the p-values, and it looks like group number 5, group number 4 and group number 5 are not significantly different. This is not less than 0.05, which is the usual threshold that we use in a statistic. So basically what this is saying, that the difference between the mean in 4 versus the mean in 5, there is almost 50% chance that they are equal to each other. That's what the p-values actually says. You want to reproduce the summary table, you can use the table command that we used before for the income group, and we want the mean of the cases and the mean of the deaths. This is kind of like a summary table. This is similar to the 2 tables that we saw before in the ANOVAs. You can also do t-tests. The t-tests are usually useful for when you only want to compare 2 groups. In this case, the t-tests do not quite apply to the income group variable because we have more than 2 groups. But just for educational purposes, I'm going to just show you how it works. The command is t-test. If you want more information, just type help t-test. The null hypothesis is that the mean number 1 is equals to mean number 2. The alternative is that they are not. We are talking about 2-sided test. So the command is t-test, and then you put the variable first, right? Now, since we have a variable that has 5 groups, we need to actually subset, and we can use that for the conditional if. Only let's compare in this case, in cases group number 3 versus group number 4, right? So basically it's t-test, daily cases. If we don't have conditionals, then this goes away. But in this case, we're going to subset. And then comma, and here you say by income group. Because we are conditioned income group only those 2 are going to show up. So select and run. And this is the output for the t-test. Basically, it gives you the summary of each of the 2 groups. The mean, the standard deviation, so on and so forth. The difference, and this is basically the null hypothesis, right? And the 2-sided test is the one in the center, this one. So this is the p-value, testing the difference between those 2. So the difference here is 6 points. We want to see whether these 6 points are significantly different. So basically the 2 means are different. And the probability that these 2 means are equal to each other, or the sum of these 2 gives 0, is actually 0%. So basically there is no way that these 2 are the same. These 2 means are the same. We can do the same thing with the deaths, but comparing groups 4 and 5. And it says here that the mean, even the difference is very small, the mean is actually significant. Now, again, this is just for educational purposes. The actual difference is not significant when we account for by the number of tests. But that's how you run a t-test. Now, in terms of linear regression, the command for that is called reg, R-E-G, short for regress. The format here is the first variable in this command is the dependent variable or the outcome variable, the y. After that, you can put all the independent variables, all the x's. In this case, we only have 1. And then you also, after the comma, make sure you add the option robust to control for heteroscedasticity. If you're not sure whether you need to add the robust option, don't worry, always add it. So you run the model, just select and run, and we get this output. At the top, you get the number of cases, you get the F statistics for the model, and this is the probability that the model is actually valid. In this case, it's valid. The R square shows you the percentage of variance that this model explains in the outcome. So basically, this model explains about 5.67% of the variance seen in daily cases. And the root MSE is basically the standard deviation of the model. You want this number to be as close to 0 as possible. Then we move into the coefficients. So basically the p-value, this p-value is testing whether this coefficient is equals to 0. So basically the probability that this coefficient is equals to 0 is basically 0%. And you can see this also in the confidence intervals. 0 is not in the range. This t-value is basically, if you divide this coefficient by this standard error, it gives you this number. And this is the p-value that is associated with that t. So basically what this says is that the coefficient is positive. We can see that as GDP per capita increases $1, the number of daily cases in terms of the per 100,000 increases 0.0006. It's small, but it's positive, significant, so there is something going on there. So one way to further analyze the relationship between these two variables, and since we are into fitting linear models, we want to see whether the original variables we need to do some sort of transformations to see whether we can linearize that relationship a little bit better. First, you need to kind of like check the distribution of each variable. For that, you can use also a histogram. So histograms are also very important graphs in statistics because it allows us to see the distribution of the data. So I'm going to run a histogram for the daily deaths variable. And you can see the daily death variable is way too skewed towards the right. So there are very few very large values, and most of them are on the lower end. Let's check GDP per capita. This one is also skewed to the right, so there are very few very rich. Let's see the trust variable. The trust variable looks a little bit better. It looks more bell-shaped, more distributed. So let's say let's get a quick scatter plot between daily 7 deaths and GDP. I think we did this before. And you can see that there is a little down line here, downward trend. Not exactly linear, but let's see if we can do something about it. Sometimes when you see this kind of distributions, we can just try to linearize the relationship by convert. I'm not saying that we have to do this on this case, but just to show how it's done in case you need to do it, we can create a log version of the variables. So in order to linearize them in this case. So we're going to use the command gen again. I'm going to call this new variable ln GDP per capita, and that's going to be equals to this function ln, the natural log of GDP per capita. So I'm going to run that, no errors. So I'm going to get the log of deaths again, and the same function ln. Now in this case, because daily deaths have a lot of zeros in the data, if we do only the log of the variable as it is, all the zeros are going to become missing. So we're going to lose data. So to keep the zeros in there, we need to rescale the variable. So the zeros become 1, and the log of 1 is 0. So everything goes back to the same scale. So the logs transformation only apply to positive numbers, so you have to be mindful of that. If you have negative, let's say the lowest value is -10, you need to take the log and you don't want to lose that value, or that value is important to you, you need to rescale. Basically, instead of adding 1, you need to add 11, right? So when you take the log, everything goes back down. So basically you are rescaling. So we're going to do the same thing for cases, and we're going to take, we're going to get the scatter plot again for these two variables to see if there is some changes in there. Okay, so we got some errors here. All right, so it says that I created that variable. Oh, I run it twice. Okay. So that's the thing. When a variable is already created, Stata gives you, hey, by the way, this variable already exists. So let me do the. So this scatter plot looks a little better. So we are, I mean, not perfect, but it provides a better perspective in terms of as GDP per capita is going up, it looks like there is an upward trend in the number of beds. So let's check the regression again, but then we're going to use the LN version of the variables. So the R squared increases a little bit from, I think, 5% to 7%. The coefficient is still significant, is still positive. Now the interpretation of this, I mean, any statistics book you can check this. The interpretation when the dependent variable is in logs and the independent variable or the outcome variable is in logs and the independent variable is in logs, this becomes the elasticity. So basically when GDP per capita increases 1%, we can see that the number of cases increases about 0.03%. So it's a positive relationship no matter what. So let's add a second variable, trust. We don't need to convert or transform trust in this case because it looks like the variable itself is in a good format. So let's check that out. Let's see how that looks like. So the R squared increased a little bit more. And then we have trust here is significant and is negative. Now, in this case, when trust increases 1 point, this is a semi-log regression when it comes to the log and no log or log level variables. So when trust increases 1 percentage point, the number of cases goes down by 0.2%. So it's kind of like you have to do the transformation, and then because this number is very small, we just multiply by 100. But if we're more like 0.10 points, you need to do a quick transformation, taking the anti-log minus 1 times 100. So it's still negative. So basically we see that overall, this it looks like the trends, the findings so far suggest that rich countries tend to have more cases, but those countries with higher level of trust in government or where the populations have higher levels of confidence in government, in the governments, the number of cases seems to go down. So remember that we have a categorical variable called income group. You can use actually that one in the regression. The only thing is you cannot enter the variable as a continuous variable as we did for GDP and trust. So we need to include that variable as dummy variables, as categorical. And that's what this I dot do. So let me run that and show you how it works. So, and we are not entering this variable as continuous because the levels 1, 2, 3, 4, 5 are not equally spaced, right? So in this case, you cannot really use it as a continuous variable, but we can use it as a dummy variable. So in this case, each one of these coefficients is a dummy. This is 1, and 0 is the group that you don't see, basically the lowest group. So here is 1, 2, 3, and it's 2, 3, 4, and 5. Group 1, the one that you don't see, is the one that serves as reference. So basically this regression is comparing group number 1 versus group number 2. It's telling us that this is basically 11 percentage points higher than the group number 1. And basically all the groups are way higher and positive than as compared to the poorest group. So that's how you read it. So let's say, for example, we add a trust variable. So we have pretty much similar effect. Trust continues to be negative as it goes higher levels of confidence, and income remains on the positive side.